latent heat energy. Latent heat energy is the amount of heat energy required to change a substance from one state of matter to another at constant temperature. Latent heat of fusion is the quantity of heat energy needed to change a solid at its melting point to liquid state, temperature remaining constant. Specific latent heat of fusion is the amount of heat energy required to change a unit mass of a solid at its melting point to liquid state without change in temperature. Specific latent heat of fusion, in terms of formula, is equal to quantity of heat energy supplied to the solid at the melting point divided by the mass of the solid. It's represented by letter L with this subscript L showing that its fusion process is equal to quantity of heat energy divided by the mass of the substance. The unit of specific latent heat of fusion is joule per kilogram. Quantity of heat energy Q is equal to mass of the substance times specific latent heat of fusion. This is equation 1. Equation 1 above is used to calculate the heat required to change a solid of mass m at its melting point to liquid state. Latent heat of vaporization is the amount of heat energy needed to change a liquid at its boiling point to vapor at constant temperature. Specific latent heat of vaporization is the quantity of heat energy required to change a unit mass of a liquid at its boiling point to vapor state, temperature remaining the same. In formula terms, specific latent heat of vaporization is equal to quantity of heat energy supplied to the liquid at boiling point divided by the mass of the liquid. This is specific latent heat of vaporization is equal to quantity of heat supplied at the boiling point divided by the mass of the liquid. Again, if we cross multiply, the heat required to change a liquid at boiling point to vapor is equal to mass times specific latent heat of vaporization. The unit of specific latent heat of vaporization of a liquid is joule per kilogram. The latent heat of fusion supplied to a solid to change it to liquid state is also given out by the liquid when it changes to the solid state. Specific latent heat of vaporization of a unit mass of matter in one state is greater than the specific latent heat of fusion of the same matter in another state. Example 1. Calculate the amount of heat energy required to convert 2 kg of ice at minus 2 degrees Celsius to water at 0 degrees Celsius. Specific heat capacity of ice is equal to 2090 joules per kilogram per degree Celsius. Specific latent heat of fusion of ice is equal to 336 kilojoules per kilogram. The options are 6,660 joules, B 8,360 joules, C 660,000 joules, D 680,360 joules. The solution to this example is as follows. Solution. The ice was initially at a temperature of -2 degrees Celsius. The heat supplied to it will first increase the temperature to the melting point of ice, which is 0 degrees Celsius. And a further application of heat energy to the ice will now change the ice to water at the same temperature of 0 degrees Celsius. Now we look at the stages to know the formula that will be needed to solve the problem. Ice at -2 degrees Celsius first increase the temperature to 0. So the heat energy required to effect that increase is calculated using mc theta. Then the second part of it, the ice at the melting point 0 degrees Celsius now changed to water at the same temperature. Then the formula needed to effect or calculate the heat that did the work is mL, where L is the latent heat of fusion of ice. By combining the two, we now get the total heat energy required to effect that transition. The calculation is as follows. The mass of ice is 2, specific heat capacity 2090, change in temperature from -2 to 0 is 2. Mass of ice 2, latent heat of fusion of ice, we are told, is 336 kilojoules per kilogram. So we have 336 times 1,000. The kilo, 1 kilo is 1,000. So if we do that, we now end up getting quantity of heat energy is equal to 8360 plus 672,000 joules of heat energy. So the quantity of heat energy required to effect the transition is 680,360 joules. By this calculation, option D is correct. Example 2. We are provided with a transition graph of naphthalene. In an experiment in which molten naphthalene is allowed to cool, the cooling curve above was obtained. The temperature 80 degrees Celsius is known as the dash. A, cooling temperature. B, boiling point. C, melting point. D, vaporization point. To answer the question given as example 2 above, we have to refer back to what we know about change of state of matter. That temperature, 80 degrees Celsius, if you observe very well, the temperature remained constant for a reasonable length of time. 1. Answer. At 80 degrees Celsius, temperature remained constant for a period of time. This must be a transition process. Let me look at it again. If it is transition process, it is either melting point or boiling point. But we are told that it's a cooling process. So the only transition temperature that involves cooling is the melting point of a solid. Melting point of a solid is obtained when the liquid form of the solid is cooled. Thus, 80 degrees above represents the melting point. Option C is correct. Example 3. Which of the following graphs clearly illustrates the temperature change which takes place as a piece of ice at minus 10 degrees Celsius is heated slowly? You have the option A, we've seen the graph. Option B is also indicated here, the temperature time graph. Option C is shown, and option D is shown. The answer to example 3 is as follows. We have to observe the graphs given and point out the necessary faults. The ice was initially at a temperature of minus 10. And when heated, the temperature will first get to 0 degrees Celsius. And at that time, that's the melting point of ice. A further application of heat will result to a constant temperature because at that time the ice will be changing to water, the liquid form of it. And the transition continues. The temperature of the water will continue. With that starting point, let's look at graph A. Graph A is wrong for the following reasons. A, no indication of minus 10 degrees Celsius in the graph. The second reason why graph A is wrong is that at a point the temperature was increasing at a fixed time, which is not possible. Temperature increased at fixed time. Is wrong. Is wrong. So option A is wrong. So let's take option B. In option B, the graph started at a low temperature, below 0 degrees Celsius, but the temperature increased indefinitely. The transition temperature where the ice melted and formed water was not given. Therefore, graph B is wrong. Wrong. Because transition point from ice to water was not indicated. So this one, we've noted that. Let's look at C. Graph C started with a temperature below 0 degrees Celsius, which is the temperature of that ice. It increased up to 0 degrees Celsius, the melting point, and it remained constant for some time. That's the time the ice was melting or changing to water. And after the formation of the water, the temperature increased again up to the boiling point where the temperature remained constant. Option C is correct. Let's look at D and see the problem with D. Graph B started with a temperature below 0, that's correct. But the temperature increased non-stop without any transition temperature from one state of matter to another beyond 0 degrees Celsius. So option D is wrong. So by this, the correct option for example 3 is C.